Tonight, we're going to talk about the most mysterious substance in the universe. And when I say mysterious, I don't mean something subtle or hard to measure. I mean something that makes up the majority of all matter in existence and that we have never directly seen, touched, or identified, not even close. Everything you've ever looked at in the night sky, every star, every galaxy, every glowing cloud of gas, represents a tiny fraction of what's actually out there. A thin sliver, a rounding error on the cosmic ledger. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. I'd love to know where you're watching from and what time it is for you. Feel free to drop your location and time in the comments below. Here's the number. Ordinary matter, the stuff made of atoms. The stuff that makes up planets and people and stars and everything you've ever encountered in your entire life, accounts for about 5% of the universe. 5%. The rest is something else. About 27% is dark matter. Another 68% is dark energy, which is a separate mystery entirely, and we'll get to that distinction. But focus on that 27% for a moment. Dark matter outweighs all the ordinary matter in the universe by roughly 5 to 1. Every star you've ever seen, every galaxy ever photographed, every atom that has ever existed anywhere, is vastly outnumbered by something we cannot observe directly, something we have no name for beyond the absence it represents. That's what makes this problem different from most problems in science. We're not trying to measure something small or distant or faint. We're trying to identify the dominant form of matter in the universe, and we don't know what it is. We know it has gravity. We can measure those gravitational effects with extraordinary precision. We can map where dark matter is concentrated, how it's distributed across galaxy clusters, how it behaves across billions of light years of cosmic structure. We can do all of that. What we can't do is tell you what it's made of. Think about what that means. Our most successful model of the universe, the model that correctly predicts the large-scale structure of the cosmos, the one that matches observations from dozens of independent experiments across completely different scales, is built around a dominant component that nobody has ever directly detected. The physics works, the predictions are accurate, and the central ingredient remains unidentified. Dark matter doesn't emit light. It doesn't absorb light. It doesn't interact with the electromagnetic force at all, which means every telescope ever built, every instrument designed to detect radiation across any wavelength, infrared, ultraviolet, X-ray, radio, none of them can see it. It's not dark in the way a shadow is dark, where something is blocking the light. It's dark in the sense that light has nothing to do with it. It passes through everything. It passes through you right now. Constantly, without slowing, without interacting, without leaving a trace. The only reason we know it's there is gravity, and gravity, as it turns out, is enough. The scale of what's missing is difficult to process. Our brains didn't evolve to handle numbers like these. When astronomers catalog the visible universe, counting up every galaxy, every star, every cloud of hydrogen between the galaxies, they arrive at a mass total that falls dramatically short of what the universe actually contains, not by a small margin, not by a factor of 2 or 3. The visible universe is a fraction of the real one. All the light we've ever detected, across the entire history of astronomy, has been telling us about that 5% sliver. The rest has been hiding in plain sight, detectable only by the way it bends the behavior of everything around it. This is the central mystery of modern cosmology, not a small gap in our knowledge, not a detail to be filled in. The majority of the matter in the universe is something we haven't identified, and the evidence for it, the evidence that forced scientists to accept its existence against considerable resistance, didn't come from particle accelerators or exotic instruments. It came from watching galaxies move. To understand what dark matter really is, we have to start with what we can actually see, start with what we know. Every night, when the sky is clear and you're far enough from city lights, you can look up and see thousands of stars. That's the visible universe from your backyard. But that's just the beginning. When astronomers point telescopes at the sky, the numbers scale up fast. The Milky Way alone contains somewhere between 100 and 400 billion stars. Stars of every size and temperature. Red dwarfs barely large enough to fuse hydrogen. Blue supergiants burning so hot they'll exhaust themselves in a few million years. Everything in between. And the Milky Way is one galaxy among an estimated 2 trillion in the observable universe. 2 trillion, each one containing hundreds of billions of stars of their own. Beyond the stars, there's gas, enormous clouds of hydrogen and helium drifting through the space between stars, the raw material that eventually collapses under its own gravity to form new ones. There are nebulae stretching hundreds of light years across. There are stellar nurseries where new stars are igniting right now. There are the remnants of dead stars, white dwarfs, neutron stars, the collapsed cores left behind after massive stars exhaust their fuel. There are planets, moons, asteroids, comets, dust. The universe, from our perspective, is extraordinarily full of stuff. It's dense with structure, dense with complexity. When the Hubble Space Telescope stared at a tiny patch of sky no larger than a grain of sand held at arm's length, it found 10,000 galaxies in that single image. 10,000 galaxies in a piece of sky you could block with a grain of sand. Here's the problem. All of it, every star, every galaxy, every gas cloud, every nebula, every planet is made of the same basic stuff. Protons, neutrons, and electrons arranged into atoms. This is what physicists call baryonic matter. It's the matter described by the standard model of particle physics. It's the matter that makes up your body and this planet and every object you've ever encountered. And when astronomers added up all the baryonic matter they could find in the universe, all the stars, all the gas, all the dust, everything detectable across the entire electromagnetic spectrum from radio waves to gamma rays, they got a number, a specific fraction of the total energy content of the universe. That fraction is about 5%. Everything we've ever seen, every telescope image ever captured, every galaxy ever cataloged in any survey, from any observatory in any wavelength of light. All of it adds up to roughly 5% of what exists. The rest is invisible to us. Not distant, not just faint, invisible. It emits no light. It absorbs no light. It reflects nothing. Conventional astronomy, which depends entirely on detecting electromagnetic radiation in one form or another, simply cannot see it. Think about what 5% actually means. If you had a room with 100 people in it, and you could only perceive 5 of them, you might still develop a pretty detailed understanding of those 5. You could describe their clothing, their movements, their conversations, but you'd be missing 95 people standing right next to you. That's the situation astronomers found themselves in. They had built extraordinary tools, radio telescopes, infrared detectors, X-ray satellites, and extended their vision across the entire electromagnetic spectrum, and they were still blind to 95% of the universe. The 27% that isn't dark energy is what we call dark matter. It has mass, it has gravity, but it produces no light of any kind, and it absorbs none either. It doesn't interact electromagnetically at all. The only fingerprint it leaves on the universe is gravitational. You cannot photograph it. You cannot image it in any wavelength. You can only detect it by watching how it pulls on things you can see. And when astronomers started doing exactly that, watching the behavior of stars and galaxy clusters and asking what the gravity implied, the numbers came back wildly, stubbornly wrong. The visible matter wasn't enough, not even close. There had to be something else out there, something massive and invisible, distributed through and around the structures we could see. The scale of the discrepancy is important to hold on to. It isn't a small rounding error. It isn't a subtle correction to an otherwise tidy ledger. The visible universe is not the universe with a small footnote of missing matter. It's more like the footnote is the visible universe. The thing we call normal, atoms, stars, planets, people, is the exotic minority. The dominant component of the universe is something we've never directly detected, never identified, never touched. Ordinary matter is the exception. Whatever dark matter is, it's the rule. Put it in a different frame. The Sun, which contains 99.86% of all the mass in our solar system, which could swallow 1.3 million Earths inside its volume, which has burned for 4.6 billion years. That star is ordinary baryonic matter. It counts toward the 5%. Every star you can see, every galaxy the Hubble has ever imaged, every atom in your body, all of it counts toward the 5%. Then there's the other 95%. Dark matter alone accounts for more than 5 times everything we've ever observed. 5 times all the stars and all the galaxies in the observable universe, in a form we've never directly seen. The question, once you see it, is impossible to ignore. Where is the rest of it? The first person to seriously grapple with this problem was a Swiss-American astronomer named Fritz Zwicky. Zwicky was not an easy man to work with. His colleagues at Caltech described him as combative, arrogant, and impossible. He called other astronomers spherical bastards, meaning from any angle you looked at them, they were still bastards. He was brilliant, and he knew it. He was also, on at least one occasion, spectacularly right when everyone else was wrong. In 1933, Zwicky turned a telescope toward a collection of galaxies known as the Coma Cluster, roughly 320 million light-years from Earth. What he found there didn't make sense. It took the rest of science about 40 years to admit he was onto something. First, you need to understand what a galaxy cluster actually is. A galaxy cluster is exactly what it sounds like. Hundreds or thousands of individual galaxies, each containing billions of stars bound together by gravity into a single enormous structure. The Coma Cluster contains over 1,000 galaxies. They're not just sitting still, they move. They orbit around the cluster's common center of mass, pulled by the gravity of everything around them. The faster those galaxies move, the more mass the cluster needs to hold them in. If the cluster didn't have enough mass, the galaxies would fly apart. They'd escape into the void between clusters and never come back. This is the basic logic behind something called the virial theorem. It's a principle from physics that relates the average kinetic energy of a system, how fast things are moving, to the gravitational potential energy holding them together. In plain terms, it tells you how much mass a system must contain based on how fast its members are moving. Zwicky used this theorem. He measured the velocities of 8 galaxies in the Coma Cluster. Then he calculated how much mass the cluster needed to keep those galaxies bound. The number he got was staggering. The galaxies in the Coma Cluster were moving at around 1,000 kilometers per second. That's roughly 620 miles per second. Using the virial theorem, Zwicky worked out what the cluster needed to weigh in order to hold those galaxies at those speeds. Then he looked at the visible matter, all the light coming from all those galaxies, and estimated the cluster's mass from that. The two numbers were wildly different. The cluster, based on how fast its galaxies moved, needed to be at least 400 times more massive than everything visible inside it could possibly account for. 400 times. Not twice as massive. Not 10 times. 400 times more massive than what the light suggested. The mass-to-light ratio was completely out of balance. For every unit of mass you could account for using visible galaxies, there had to be 400 units of mass you couldn't see at all. Zwicky recognized this immediately. He wasn't confused by the math. He understood what the math was telling him. There was matter in that cluster, enormous quantities of matter, that wasn't producing any light. It wasn't glowing. It wasn't visible. It was just there, exerting gravity, holding everything together, and showing up nowhere in any telescope image ever taken. He called it Dunkel Materiae, dark matter. The name is almost disarmingly simple. Dark, because it produced no light. Matter, because it clearly had mass and gravity. Zwicky published his findings and put the term into the scientific literature. He laid out the evidence. He explained the discrepancy. He described a universe that contained far more mass than anyone could see, and then the broader scientific community looked at his work and essentially shrugged. Part of this was Zwicky himself. When you spend years calling your colleagues spherical bastards, they're not especially eager to champion your ideas. His personality made it easy for people to dismiss him. Part of it was the scale of the claim. Zwicky wasn't suggesting a minor correction to existing theory. He was suggesting that the vast majority of the matter in a galaxy cluster was completely invisible. That's not a small ask. That's a fundamental rethinking of what the universe contains. Scientists are cautious about claims that large, and for good reason. There's also the matter of alternatives. Maybe the virial theorem didn't apply cleanly to a system as complex as a galaxy cluster. Maybe the measurements of galaxy velocities carried enough uncertainty to explain the gap. Maybe the cluster wasn't in a stable, bound state at all. There were enough possible objections that dismissing Zwicky's conclusion felt scientifically reasonable at the time. Not proven wrong, just unconfirmed. Just one astronomer's puzzling result from one cluster, waiting for more data. So the finding sat. Decades passed. The 1930s became the 1940s, then the 1950s, then the 1960s. New telescopes were built. New galaxies were catalogued. New clusters were studied. The question of what held the Coma Cluster together didn't disappear, but it didn't dominate anyone's research agenda either. It was one of those problems that gets filed away under things we don't fully understand yet, without urgency, without follow-up, without the weight it deserved. Zwicky kept working. He made other contributions. He moved on to other problems. But the dark matter question he'd raised in 1933 sat largely untouched, waiting for someone to take it seriously enough to push harder. Nobody believed him. The discovery that finally forced the scientific world to pay attention came from an astronomer named Vera Rubin. It was the late 1960s and early 1970s. Zwicky had raised his alarm decades earlier. His math was solid, his data was real, and the scientific community had spent 30 years largely ignoring him. Rubin was working at the Carnegie Institution of Washington alongside a physicist named Kent Ford. Ford had built an extraordinarily sensitive spectrograph, a device capable of measuring the velocities of stars in other galaxies with a precision that simply hadn't existed before. Together, they turned that instrument toward the Andromeda Galaxy, the large spiral sitting about 2.5 million light-years away, the nearest major galaxy to our own. What they found on their readouts made no sense. To understand why it made no sense, you have to understand what the readouts were supposed to show. Think about our own solar system. Mercury, the innermost planet, completes an orbit in 88 days. It moves at roughly 107,000 miles per hour. Neptune, out near the edge, takes 165 years to complete a single orbit. It moves at about 12,000 miles per hour. The planets farther from the sun move slower. That's not a coincidence. That's gravity. The sun's gravitational pull weakens with distance. The farther you are from the source of gravity, the less pull you feel, and the slower you orbit. This relationship is described precisely by Newton's laws, and it works. We use it to navigate spacecraft. It predicted the existence of Neptune before anyone had seen it. It's one of the most tested ideas in the history of science. Now apply that same logic to a galaxy. A spiral galaxy has most of its visible mass concentrated in the bright central bulge. Stars, gas, and dust crowd together in the middle. As you move out toward the edges of the disk, the density of visible matter drops, so the stars near the outer edges of a spiral galaxy should orbit the galactic center more slowly, just like Neptune orbits the sun more slowly than Mercury does. The math is the same. The physics is the same. The rotation curve, a graph plotting orbital velocity against distance from the center, should rise near the core and then fall off, drop, taper away as you move outward. That's what anyone trained in physics would have predicted, and that's what every astronomer expected to see. That is not what Rubin and Ford found. The rotation curves were flat, not roughly flat, Not approximately flat with some deviation they could explain away. Flat. Stars at the outer edges of the Andromeda Galaxy were orbiting just as fast as stars much closer to the center. The velocity didn't drop. It stayed stubbornly, inexplicably constant all the way out to the edge of the visible disk and beyond. The outer stars were moving so fast that by any conventional accounting, they should have been flung out into intergalactic space. Nothing visible could hold them in those orbits. The numbers simply didn't work if you only counted the light-emitting matter. Rubin recognized what she was looking at. The only explanation that fit the data was that there was mass out there that she couldn't see. Not a little bit of extra mass, an enormous amount, distributed not just inside the visible disk of the galaxy, but extending far beyond it in a vast, invisible halo surrounding the entire system. The visible galaxy, all those hundreds of billions of stars, would have to be embedded inside a much larger cloud of something dark and massive. That invisible component would need to contain several times more mass than all the visible stars combined. Here's what makes this different from what Zwicky did. Zwicky had looked at a cluster of galaxies and inferred missing mass from the motion of those galaxies through the cluster. It was a compelling argument, but it was one system, one measurement, and it left room for debate. Rubin and Ford didn't stop at Andromeda. They kept going. They measured the rotation curves of spiral galaxy after spiral galaxy, different sizes, different luminosities, different distances from Earth, different environments. Galaxy after galaxy showed the same thing, flat rotation curves, every single one. By the time they published their systematic survey in 1980, they had measured dozens of galaxies and the pattern held across all of them. This wasn't a quirk of one unusual system. It wasn't a measurement error. It was a universal feature of spiral galaxies everywhere they looked. The numbers Rubin was working with were stark. A typical spiral galaxy's visible disk might extend perhaps 50,000 light-years from the center. But to explain the rotation curves, the invisible mass halo had to extend several times further than that, hundreds of thousands of light-years. And the total mass in that invisible component? Roughly 5 to 10 times the mass of all the stars you could see. 5 to 10 times. The visible galaxy was a small fraction of its own total mass. What we had been calling a galaxy, that beautiful pinwheel of stars, was really just the luminous center of something vastly larger and invisible. The scientific community could not ignore this the way it had ignored Zwicky. The data was too systematic. The effect was too large. The measurements were too precise. Within a few years, the concept of dark matter moved from the fringe into the mainstream. Rotation curves became the standard evidence cited in textbooks. Rubin's work appeared in journals, at conferences, in the lectures of astronomers who had previously dismissed the idea entirely. What she had found was a shadow, not the dark matter itself, just its gravitational fingerprint, pressed into the motion of every spiral galaxy she had ever pointed a telescope at. Something was out there holding those galaxies together, and it wasn't anything we could see. So what exactly is dark matter? That sounds like a simple question. It isn't. After nearly a century of study, we can describe dark matter precisely in terms of what it does. What it actually is remains unknown. But let's start with what we do know, because what we know is genuinely remarkable. Dark matter does not emit light, not in the visible spectrum, not in infrared, not in ultraviolet, not in X-rays, not in radio waves. Across the entire electromagnetic spectrum, it produces nothing, no glow, no shimmer, no faint signal of any kind. That's not a limitation of our instruments. We've looked with everything we have. The silence is real. Dark matter also does not absorb light. When light passes through a region of space filled with dark matter, the light keeps going. It doesn't scatter, it doesn't dim. It passes through as if nothing is there. This is why the name is fitting. It's not dark in the way a shadow is dark, something blocking light from reaching you. It's dark because it has no relationship with light at all. It doesn't interact with the electromagnetic force in any way we can measure. And the electromagnetic force is how almost everything we know about the universe gets communicated to us. Here's what most people don't realize about that. Every instrument ever built, every telescope, every camera, every spectrometer works by collecting electromagnetic radiation. Light, radio waves, X-rays, they're all the same thing at different energies. Our entire picture of the cosmos is an electromagnetic picture. Dark matter sits completely outside that picture. It's like trying to read a book while only being able to see one color, and dark matter is written in all the others. But dark matter has mass. That's the one thing it cannot hide. Mass creates gravity. Gravity reaches across space without requiring any other interaction. And gravity is the only fingerprint dark matter leaves behind. It was gravity that Zwicky noticed in the Coma Cluster. It was gravity that Vera Rubin found baked into the rotation curves of spiral galaxies. Every piece of evidence for dark matter is, at its core, a gravitational measurement. Something is pulling on things it shouldn't be able to pull on. Something is bending light around regions of space that appear empty. That something has mass, and lots of it. Dark matter has 4 properties that physicists have worked out from observations. First, it's cold. Not temperature cold, but cold in the technical cosmological sense. It means dark matter moves slowly compared to the speed of light. Particles that move close to light speed are called hot, and hot dark matter causes big problems. It would have streamed out of density fluctuations in the early universe, smoothing everything out. You wouldn't get the filaments and galaxy clusters and large-scale structure we actually observe. Cold dark matter moves sluggishly. It clumps. It forms halos. The structure of the universe matches cold dark matter predictions very well. Second, dark matter is collisionless. When dark matter particles pass through a region containing other dark matter particles, or through a region containing ordinary matter, they don't slow down. They don't interact. They keep going. The bullet cluster demonstrates this directly. 2 clusters of galaxies collided, and the dark matter passed straight through the collision like it wasn't there. Ordinary matter, gas and plasma, slammed together and slowed down. Dark matter kept moving. That behavior tells you something fundamental about what dark matter is. Third, it's stable. Dark matter has been in the universe for 13.8 billion years. Whatever these particles are, they haven't decayed into other particles. They haven't transformed into radiation. They've just persisted, holding the same gravitational influence across the entire history of the cosmos. Any dark matter candidate has to be something that can survive that long without changing. Fourth, dark matter is non-baryonic. It is not made of protons, neutrons, or electrons. It is not atoms or molecules. It is not any ordinary matter in an unusual state. We can say this with confidence because Big Bang nucleosynthesis, the process that created the first hydrogen, helium, and lithium in the early universe, sets strict limits on how much baryonic matter can exist. The math gives you about 5% of the universe. Dark matter is 27%. Those 2 numbers cannot be the same substance. They are completely separate components of reality. So when you put this all together, what you have is a form of matter that is invisible across all wavelengths, passes through ordinary matter without interaction, moves slowly, persists indefinitely, and is made of something entirely outside the periodic table. The name dark matter is accurate in the sense that it is genuinely invisible. It's misleading in the sense that it makes this stuff sound like a simple absence of light, when what we're actually describing is a fundamentally alien category of substance that makes up more than 1/4 of everything that exists. We know it's there. We know how much of it there is. We know several things about how it behaves. We can measure its effects with extraordinary precision, but we have never directly captured it, touched it, or seen it. Before we talk about what dark matter might be, it helps to understand what it definitely isn't. The most obvious guess is ordinary matter we just can't see. Space is enormous. There's plenty of room for things to hide out there. Rogue planets, dead asteroids, cold rocks drifting between the stars with no sun to light them up. It's a reasonable thought. The problem is mass. Even if you count every rock, every dead comet, every frozen object in the dark between galaxies, the numbers don't come close, not even remotely close. The total mass of all that material is a rounding error compared to what dark matter needs to be. Planets and asteroids aren't the answer. What about gas? Cold gas clouds are real. They exist in enormous quantities between stars, between galaxies, spread through the universe in diffuse halos. And for a moment, that seems promising. Cold gas is dark. Cold gas has mass. But here's what most people don't realize. We can detect cold gas. Radio telescopes pick up the 21-centimeter emission line from neutral hydrogen, a specific wavelength of radio waves that hydrogen atoms produce naturally. Astronomers have mapped cold gas across the universe with extraordinary precision. When they add it all up, it doesn't account for the missing mass. Not even close. The dark matter is still there, still unaccounted for. So then maybe compact objects, black holes, neutron stars, white dwarfs, brown dwarfs, failed stars that never ignited. Astronomers grouped all of these under a single name, MACHOs, which stands for Massive Astrophysical Compact Halo Objects. These are real things. They exist. And the idea was straightforward. Maybe the dark matter halos surrounding galaxies are just packed with these dim, dense objects too faint to see directly. The problem is that we have a way to test this. When a MACHO passes in front of a distant star, gravity bends the star's light, briefly making it appear brighter. This is called microlensing. Surveys like MACHO, Eros, and OGLE spent years scanning millions of stars, watching for these brightening events. They found some, but not enough. Not nearly enough. MACHOs could account for a small fraction of the dark matter in our galaxy's halo. Not most of it. Not even a significant portion of it. There's a deeper problem with all of these explanations. They all involve ordinary matter. Protons, neutrons, the same building blocks that make up stars, planets, and you. Cosmologists call this baryonic matter. And here's where Big Bang nucleosynthesis closes the door almost completely. In the first few minutes after the Big Bang, the universe was hot and dense enough for nuclear fusion to occur. Hydrogen fused into helium, helium into trace amounts of lithium and beryllium. The ratios of these light elements produced in those first few minutes are exquisitely sensitive to how much baryonic matter was present. Measure the ratios today, and astronomers have done this with remarkable precision, and you can calculate exactly how much baryonic matter the universe started with. The answer is around 5% of the total energy content of the universe. All the protons and neutrons that have ever existed or ever will exist represent just 5%. Dark matter is 27%. Whatever dark matter is, it is not baryonic. It is not made of protons and neutrons. The universe simply didn't make enough of those. That rules out one last candidate people sometimes raise, neutrinos. Neutrinos are real particles. They're produced in nuclear reactions constantly, including in the core of the sun. Trillions of them pass through your body every second. They barely interact with ordinary matter at all, which makes them seem like a natural dark matter candidate. They have a tiny mass. They're extraordinarily abundant, but they have a fatal flaw. They move fast, very fast, near the speed of light in the early universe. Fast-moving particles don't clump easily under gravity. They stream freely through space, washing out the small-scale density fluctuations that eventually grew into galaxies. A universe dominated by neutrinos would look completely different from the one we actually see. Structures would be smeared out. Small galaxies would form last, not first. The observed large-scale structure of the universe, the filaments, the voids, the galaxy clusters. All of it fits cold, dark matter, not hot. Neutrinos are ruled out as the dominant component. Each candidate fails in its own way. Too little mass, detectable after all, not enough of them, made of the wrong stuff. Moving too fast, the process of elimination leads somewhere uncomfortable. Whatever dark matter is, it doesn't emit light. It doesn't interact electromagnetically. It isn't made of protons and neutrons. It isn't any particle we've ever directly detected. It isn't anything currently predicted by the standard model of particle physics. Whatever dark matter is, it's something genuinely new. Here's a number worth sitting with for a moment. 5%. That's the fraction of the universe made of ordinary matter. Atoms, molecules, protons, neutrons. Everything you've ever seen or touched or measured. Every planet, every ocean, every star burning in the night sky. Every person who has ever lived. All of it adds up to 5% of what exists. The rest is something else entirely. 27% is dark matter, the invisible substance we've been working through in the previous sections. The thing that holds galaxies together and leaves no trace on any detector we've ever built. And then there's the remaining 68%. That's dark energy. It isn't dark matter with a different name. It isn't the same thing at all. Dark energy is something stranger, a property of space itself, a force driving the universe to expand faster and faster with every passing second. Dark matter pulls things together through gravity. Dark energy pushes the universe apart. They are different problems with different behaviors and different implications, and conflating them is one of the most common mistakes people make when first encountering this subject. So the accounting goes like this: 5% ordinary matter, 27% dark matter, 68% dark energy. That's 100% of everything. And the slice we actually understand, the slice built from atoms obeying the physics we teach in classrooms, is 5%. Not the majority, not even close. A thin sliver at the edge of a composition we cannot fully explain. Take a moment with the dark energy number. 68%, more than 2/3 of the entire energy content of the universe, is in a form that physicists can measure only by watching its effect on the expansion rate of space. We don't know what it is. We don't know where it comes from. The equations accommodate it. Einstein's cosmological constant acts as a mathematical placeholder. But nobody can tell you what dark energy actually is at a fundamental level. It was only confirmed in 1998 when two independent teams of astronomers studying distant supernovae found that the universe wasn't just expanding, it was accelerating. Something was pushing outward. That discovery earned the Nobel Prize in Physics in 2011, and it remains unexplained today. The model that holds all three components together is called lambda CDM. Lambda stands for the cosmological constant, the mathematical term for dark energy. CDM stands for cold, dark matter. It's the standard cosmological model, the framework that professional cosmologists use to make predictions about the universe. And it works extraordinarily well. Lambda CDM correctly predicts the large-scale structure of the cosmos, the way galaxies cluster into filaments and sheets and enormous voids. It correctly predicts the pattern of temperature fluctuations in the cosmic microwave background. It correctly predicts how galaxy clusters grow over time. Every major observation we've made at cosmological scales snaps cleanly into place within this model. It is, by almost any measure, one of the most successful scientific models ever constructed. And yet its two dominant components are mysteries. The model works. The components it's built around are unknown. That tension sits at the heart of modern cosmology, and it doesn't go away. Here's what that means in practical terms. Every image ever taken by the Hubble Space Telescope, every distant galaxy, every glowing nebula, every cluster of hundreds of billions of stars, all of that is drawn from the 5%. Astronomers have cataloged hundreds of millions of galaxies. They've mapped the distribution of matter across billions of light years. They've taken the spectrum of stars too distant to see with the naked eye. All of it, Every instrument ever built, every observation ever recorded, every object ever named, belongs to the minor fraction. The dominant component of the universe has never appeared on a photograph. It has never registered on a spectrograph. It has never triggered a single pixel in any camera pointed at the sky. The 5% is not nothing. It gave us everything we know about the universe, every physical law we've derived, every cosmological principle we've tested. But the 5% is also a narrow window. We built our entire picture of the cosmos from a fraction we can observe, while the vast majority remains invisible. There's something genuinely disorienting about this once it sinks in. Science isn't just saying we haven't looked hard enough or that our telescopes need to be bigger. It's saying that the universe is dominated by substances that are categorically different from everything we've ever directly studied. Ordinary physics, the kind that describes how atoms behave and how light travels, governs a sliver. The universe runs mostly on something else. Lambda CDM captures this reality in its equations, and it makes predictions that hold up. But a model can accommodate a component without explaining it. We know dark energy exists because the expansion of space accelerates. We know dark matter exists because gravity behaves in ways ordinary matter cannot explain alone. The numbers are precise: 27%, 68%, 5%. Those figures didn't come from guesses. They came from independent measurements that all converged on the same answer. The precision is real. The explanation is missing. All the stars, all the galaxies, all the planets and moons and gas clouds and everything we've ever observed represents just 5% of what exists. One of the most powerful tools astronomers have for studying dark matter doesn't involve detecting dark matter directly at all. It works because of something Einstein figured out over a century ago. General relativity tells us that mass warps space-time. Not just mass we can see, all mass. And when light travels through warped space-time, it follows the curve. Its path bends. The light doesn't know it's bending. It's just following the geometry of the space it's moving through. Here's what that means in practice. When you look at a distant galaxy through a powerful telescope, the light from that galaxy has been traveling for millions or billions of years before it reaches the detector. Along the way, it may have passed close to an enormous concentration of mass, a galaxy cluster sitting between us and the source. That cluster warps the space around it. The light from the galaxy behind it follows those curves. By the time it reaches us, the image is distorted, stretched, sometimes split into multiple copies, sometimes bent into arcs that curve around the cluster like streaks of paint. Astronomers call this gravitational lensing, and it's one of the most remarkable phenomena in observational astronomy. The key insight is this: the amount of distortion tells you how much mass is doing the bending. More mass means stronger warping. Stronger warping means more distortion. You can work backwards from the shape of the distorted images to calculate the total mass of the cluster producing the effect. Not just the visible mass, all of it. The stars, the gas, the dust, and anything else that has gravity, including dark matter. There are two distinct versions of this effect. The first is called strong lensing. This is what you see when the alignment is nearly perfect, when the background galaxy, the intervening cluster, and Earth are arranged close to a straight line. In those cases, the lensing is dramatic. The background galaxy gets smeared into a bright arc curving around the cluster. Sometimes you get multiple images of the same galaxy appearing in different positions around the lens. Sometimes the light bends into a nearly complete ring, called an Einstein ring. These are striking, obvious, unmistakable distortions. They show up directly in telescope images, and when astronomers calculate the mass needed to produce them, the numbers are far too large to be explained by the visible matter in the cluster alone. The second version is subtler. Weak lensing doesn't produce dramatic arcs. It produces tiny, almost imperceptible distortions in the shapes of background galaxies. Each individual distortion is far too small to interpret. Any single galaxy might just be naturally elliptical. But dark matter doesn't just affect one galaxy, it affects everything behind the cluster, across a wide patch of sky. So astronomers look at thousands of background galaxies at once and measure the statistical pattern of their shapes. If the shapes are randomly oriented, there's no lensing signal. If they're systematically stretched in the same direction, that alignment is the signature of a mass distribution bending the light. From those patterns, you can map where the mass is and how it's distributed across the cluster. What those maps show is striking. The mass is not where you'd expect it to be if gravity only followed ordinary matter. Galaxies have extended halos of mass that reach far beyond their visible boundaries. In a typical galaxy cluster, the mass extends well past any region that emits detectable light. You might have a compact core of bright galaxies surrounded by hot X-ray emitting gas, but the gravitational lensing signal keeps reaching outward into empty-looking space. The dark matter halo doesn't stop at the edge of the galaxy. It doesn't stop at the edge of the galaxy cloud. It keeps going. Think about what you're actually measuring here. You're using the bending of light from galaxies billions of light years away to trace the outline of something you cannot see at all. You're reading the shadow of an invisible structure. The visible matter is like a small cluster of lights sitting in the middle of an enormous, dark, gravitationally dominant halo that holds the whole system together. Take away the lensing data and you'd have no idea the halo is there. Add it back in, and the picture changes completely. The technique has become increasingly precise over time. Early lensing measurements had large uncertainties. Modern surveys use hundreds of thousands of background galaxies, matched to detailed models of their expected shapes, corrected for telescope distortions and atmospheric effects. The resulting mass maps have fine enough resolution to show structure inside clusters, to trace filaments of dark matter connecting neighboring clusters, to reveal the three-dimensional architecture of something that emits no light at all. Here's what most people don't realize about these maps. The visible matter, the stars, the gas clouds, all the things that glow, represents a relatively small fraction of the total mass being mapped. The dominant component, the thing that drives most of the lensing signal, is the dark matter. It's not a correction or a footnote. It's the majority. In many clusters, visible matter is a minority sitting inside a much larger dark matter structure that you can only see through its gravitational footprint. Gravitational lensing gave astronomers something they didn't have before, a way to map dark matter's location independently of any assumptions about what dark matter is. You don't need to know the particle. You don't need to know the physics. You just need light and geometry. And the geometry keeps showing the same thing. Something massive, invisible, and dominant is out there shaping the universe we can see. And then came the bullet cluster. In 2006, two galaxy clusters collided. Not gently, not slowly. These were two of the largest structures in the universe, each containing hundreds of galaxies and vast clouds of superheated gas, slamming into each other at millions of miles per hour. The event happened about 3.8 billion light-years from Earth. The light from that collision has been traveling toward us ever since. And what astronomers found when they studied it changed the dark matter debate permanently. To understand why the bullet cluster matters, you need to know what a galaxy cluster is actually made of. Most people imagine a cluster as just a collection of galaxies. But the galaxies themselves are almost beside the point. The bulk of the ordinary matter in a cluster, somewhere around 80 to 90% of it, isn't in the stars at all. It's in a vast cloud of hot gas that fills the space between the galaxies. This gas is superheated to tens of millions of degrees. It glows in X-rays. You can see it with an X-ray telescope. It's real, it's massive, and it's the dominant form of ordinary matter in the cluster. When two clusters collide, the galaxies inside them mostly pass through each other untouched. Galaxies are so spread out, the distances between individual stars so enormous that actual collisions between stars are extraordinarily rare. The galaxies just drift through each other like two swarms of bees moving in opposite directions. But the gas clouds can't do that. Gas interacts electromagnetically. When the two gas clouds meet, they push against each other. They slow down. They pile up in the middle of the collision zone. This is what you'd expect. This is physics working exactly as it should. Now here's what happened in the bullet cluster. Astronomers used the Chandra X-ray Observatory to map where the hot gas ended up after the collision. It was piled up in the center, just as expected. A compressed, glowing region of ordinary matter concentrated right where the two clusters met. Then they used gravitational lensing, the technique we talked about earlier, to map where the total mass was. And the mass was not where the gas was. The mass was in two separate clumps, one on either side of the collision zone, far ahead of where the gas had piled up. Think about what that means. The gas, all that ordinary matter, got slowed down by the collision and bunched together in the middle. But whatever was carrying most of the mass kept moving. It passed straight through the collision without slowing down. It didn't pile up. It didn't interact. The two mass clumps traveled ahead of the gas, as if the collision had barely happened at all. This is the signature of dark matter. Particles that don't interact electromagnetically, that don't experience friction, that barely interact with anything except through gravity. When ordinary matter collides and sticks and slows, dark matter just keeps going. The two components of the cluster, the ordinary matter and the dark matter, physically separated during the collision. You can see them decouple. The ordinary matter is here. The dark matter is over there. They are in different places, different measurable, mappable places in the sky. Astronomers had spent decades arguing about indirect evidence. Rotation curves, velocity dispersions, gravitational lensing of static clusters. All of it was compelling. None of it was a smoking gun. The bullet cluster was as close to a smoking gun as anyone had ever seen. Here was a system where the dynamics of the collision had actually pulled ordinary matter and dark matter apart, leaving them sitting in different locations, both mapped independently by different instruments using different methods. It was, in the words of many researchers, the most direct evidence for dark matter ever obtained. The result hit hard for another reason. At the time, some physicists were still holding out hope that modified gravity could explain away the need for dark matter. If you tweaked the laws of gravity at very low accelerations, maybe you didn't need any invisible matter at all. But modified gravity can't produce what the bullet cluster shows. In a modified gravity scenario, the gravitational signal should track the ordinary matter. It should be centered on the gas. It isn't. The mass is displaced from the gas by millions of light years. No modification to gravity can move the gravitational signal away from the matter producing it. The bullet cluster didn't just support dark matter. It put serious pressure on the most developed alternatives. There's one more thing worth mentioning here. A galaxy called NGC 1052DF4. It's about 45 million light years away, and when astronomers studied it closely, they found something unusual. It seemed to be almost completely missing its dark matter. A galaxy without its dark matter halo is a strange thing. The explanation, pieced together by Hubble observations, was gravitational stripping. A massive neighboring galaxy had passed close enough to pull the dark matter out of NGC 19052DF4 through tidal forces. The dark matter had been redistributed. The galaxy left behind was slowly being torn apart, its stars beginning to disperse with nothing to hold them in place. That finding matters for a specific reason. Dark matter, in this case, behaved like a physical substance that could be moved. It responded to gravitational forces from a nearby object. It was stripped away and scattered, leaving the host galaxy structurally compromised. That is not the behavior of a mathematical abstraction. That is the behavior of something real, something that occupies space, responds to forces, and can be separated from the ordinary matter it was previously associated with. The bullet cluster had shown you dark matter leaving ordinary matter behind. NGC 1-052DF4 showed you ordinary matter left behind without its dark matter. Two sides of the same story. The dark matter had passed right through, invisible, untouched, indifferent to everything except gravity. There's another way scientists know dark matter exists, and it comes from the oldest light in the universe. About 380,000 years after the Big Bang, the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before that moment, the universe was a dense, opaque plasma. Light couldn't travel freely through it. It was trapped, constantly scattering off charged particles, unable to go anywhere. Then, in a relatively brief window of cosmic time, the plasma cleared. The universe became transparent, and all that light, pent up and compressed for hundreds of thousands of years, streamed outward in every direction. That light is still traveling today. It has been traveling for 13.8 billion years. By now, it has cooled dramatically, stretched by the expansion of space from visible light down to microwave radiation. The temperature is just 2.7 Kelvin, barely above absolute zero. We call it the cosmic microwave background, or CMB. It fills the entire sky. Every direction you point a sensitive detector, there it is. Astronomers first detected it in 1965, almost by accident. Two physicists at Bell Labs picked up a persistent noise in their antenna and couldn't explain it. That noise turned out to be the relic glow of the Big Bang itself. The discovery was so significant it earned a Nobel Prize. But detecting it was only the beginning. The real information was buried in the fine structure, in tiny variations in temperature from one spot on the sky to another. Satellites were built to map those variations with precision. COBE launched in 1989, WMAP followed in 2001, and in 2009, the Planck satellite went up and produced the most detailed map of the CMB ever made. Here's what those maps revealed. The temperature of the CMB is almost perfectly uniform across the whole sky. Almost. There are fluctuations, tiny differences from one patch to another. Those fluctuations are 1 part in 100,000. That's a variation of 0.001%. Extraordinarily subtle. But those variations are not random noise. They have structure, patterns, peaks and troughs. And those patterns encode the composition of the universe at the moment that light was released. Think about what that means. The CMB is a snapshot, a photograph taken 380,000 years after the Big Bang, capturing the state of the universe before any galaxy ever formed, before any star ever ignited. And written into that photograph, in the statistical pattern of hot and cold spots, is information about exactly what the universe was made of at that moment. Physicists can calculate what those patterns should look like if the universe contained a certain mixture of ordinary matter, dark matter, and dark energy. Then they compare those predictions to the actual measurements. The fit either works or it doesn't. Without dark matter, the patterns don't match. The peaks come out at the wrong heights. The troughs land in the wrong places. The acoustic oscillations, the pressure waves that were moving through the early universe like sound waves through a fluid, are sensitive to how much gravitational mass was pulling on the plasma at the time. Dark matter doesn't interact with the plasma. It doesn't get pushed around by radiation pressure. It just sits there, exerting gravity, anchoring the fluctuations. Its presence changes the pattern in ways that are mathematically precise and observationally testable. Without it, the predicted CMB doesn't look like the measured CMB. The Planck data gives a best fit of about 27% dark matter by total energy content of the universe. That's not a rough estimate. The measurement is tight. The uncertainty is small. And here's the part that's genuinely difficult to dismiss. That number, derived from ancient light using satellite instruments and computational models, matches the number you get from studying how fast stars orbit inside individual galaxies. It matches the number you get from watching light bend around galaxy clusters. It matches the number from the bullet cluster. These are completely independent measurements. Different phenomena, different instruments, different research teams, different physical processes. Galaxy rotation curves probe scales of tens of thousands of light years. Gravitational lensing works on scales of millions of light years. The CMB is a measurement of the entire observable universe 13.8 billion years ago. They are as different as measurements can get, and yet they all come back with the same answer. That convergence is what makes the dark matter case so hard to argue against. Any single measurement can have systematic errors. Any single observational technique can be misunderstood or misapplied. But when 6 different approaches, developed independently over decades, using instruments that have nothing to do with each other, all land on the same number, something real is being measured. The universe is telling us the same thing over and over again, in different languages, from different epochs of time, across different scales of distance. Every independent measurement, from individual galaxies to galaxy clusters to the relic radiation of the Big Bang itself, keeps pointing to the same answer. When physicists try to figure out what dark matter is actually made of, the particle they keep coming back to is called a WIMP. That stands for Weakly Interacting Massive Particle. It's a name that tells you almost everything you need to know about what this thing is supposed to be. Massive means it has significant mass. Weakly interacting means it barely responds to the world around it. And that word weakly is doing a lot of work in that sentence. In physics, weakly interacting doesn't just mean it interacts a little. It refers to something specific. The weak nuclear force is one of the 4 fundamental forces of nature, alongside gravity, electromagnetism, and the strong nuclear force. The weak force governs radioactive decay. It's responsible for certain kinds of nuclear reactions, including some of the ones that power the sun. WIMPs would interact through the weak force and through gravity. That's it. They would be completely invisible to electromagnetism, which means no light, no radio waves, no X-rays. Nothing on the electromagnetic spectrum would affect them at all. They wouldn't emit photons. They wouldn't absorb them. They'd pass through ordinary matter the way a ghost passes through a wall, not because they're not real, but because the forces that bind ordinary matter together simply don't apply to them. Now, here's what makes WIMPs so compelling. It isn't just that they'd be invisible. Lots of hypothetical particles are invisible. What makes WIMPs special is something physicists call the WIMP miracle, and that name is completely earned. Here's what the miracle actually is. If you take the known physics of the early universe and you ask the question, what happens to a particle with the mass of roughly a proton up to about 1,000 times that mass if that particle was produced in the hot, dense conditions right after the Big Bang? You can calculate how many of those particles would survive to the present day. You work through the thermal equilibrium in the early universe. You account for the rate at which these particles would annihilate each other as the universe cools and expands. You run the numbers, and the answer you get matches the observed dark matter abundance today. Not approximately, not in the right ballpark. It matches, without adjusting any free parameters, without fine-tuning the calculation to force the result you want. The math just works out. If a particle like that exists, there should be exactly as much of it left today as the universe actually contains in dark matter. That's the miracle. 2 completely separate lines of reasoning, one from particle physics, one from cosmology, converge on the same number without anyone designing them to. Think about what that means. You're not inventing dark matter to explain rotation curves. You're deriving the abundance of a new particle from thermal physics in the early universe, and the number that falls out is the number astronomers need it to be. That kind of coincidence is exactly the sort of thing that makes physicists think they're onto something real. The WIMP miracle became even more exciting because of where it pointed. In the 1980s and 1990s, particle physicists were developing a theoretical extension of the Standard Model called supersymmetry. The Standard Model is the framework that describes all known particles and forces, and it works extraordinarily well, but it has gaps. It doesn't include gravity in a fundamental way. It doesn't explain why certain constants have the values they do. Supersymmetry was proposed as a possible solution to some of these problems. The core idea is that every particle in the standard model has a partner particle, a supersymmetric companion. Electrons have selectrons, quarks have squarks. The partners are heavier, and they haven't been directly observed, but the mathematics of supersymmetry is remarkably elegant. Here's where dark matter enters. In most supersymmetric models, there's a lightest supersymmetric particle. It can't decay into anything lighter because there's nothing lighter to decay into. So it's stable. It survives indefinitely. This particle, in the most widely studied supersymmetric models, is called the neutrino. The neutrino would be massive. It would be stable. It would interact via the weak force and gravity. It would be completely invisible to electromagnetism. It would have been produced in the hot early universe and survived in exactly the right abundance. It was a WIMP. The particle that dark matter physicists were looking for and the particle that supersymmetry theorists had independently derived were apparently the same thing. Two separate branches of physics developed for completely different reasons pointed at the same candidate. That's not something you can easily dismiss. The neutrino became the most studied dark matter candidate in history. Experiments were designed around it. Detectors were built to find it. The search has been going on for decades, and so far, nothing. The underground detectors have come up empty. The Large Hadron Collider has smashed protons together at energies high enough to produce supersymmetric particles if the simplest models were correct, and no supersymmetric particles have appeared. The parameter space where the most natural neutralino candidates would live has been almost entirely searched. Almost. Not entirely. There are still regions of allowed mass and interaction strength that haven't been fully explored. The WIMP hypothesis isn't dead, but it's been under significant pressure. Each null result from a major experiment forces the surviving models into narrower and narrower corners. Some physicists still think the neutralino is out there. The detectors keep improving. The next generation is already running. There's still room for a WIMP to be hiding just beyond the current sensitivity of our instruments, in a region of parameter space we haven't fully reached yet. The WIMP miracle is still real. The coincidence is still striking. The theoretical motivation hasn't gone away just because the searches haven't found anything yet. But the elegance of the prediction and the silence of the detectors exist in a growing tension that's hard to ignore. It was almost too good to be true, and in science, when something seems too good to be true, that's usually worth paying attention to. The other major candidate is a particle so small and so light, it makes a WIMP look like a boulder by comparison. WIMPs, remember, have masses somewhere between 1 and 1,000 times the mass of a proton. The axion is different. It's potentially 10 trillionths the mass of an electron. That's not a small difference. That's a difference so extreme it barely fits inside the same conceptual category. And yet the axion is one of the most serious dark matter candidates in all of physics. Not because someone went looking for dark matter and found it, but because someone went looking for something else entirely, and the axion showed up anyway. To understand where the axion came from, you have to understand a problem in particle physics called the strong CP problem. The strong nuclear force is one of nature's 4 fundamental forces. It holds the nuclei of atoms together. It governs a whole class of particles called quarks. And according to the mathematics, it should violate something called charge parity symmetry. CP symmetry is basically the idea that the laws of physics should behave the same way if you swap a particle for its antiparticle and mirror its position in space. Some forces violate this. The weak nuclear force does, but the strong force, as far as every experiment has ever shown, doesn't. Not even a little bit. The mathematics allows it to violate CP symmetry by a large amount. The measurements say it doesn't. That gap between what the equations permit and what nature does is the strong CP problem. Why is the strong force so perfectly symmetric when there's no obvious reason for it to be? In 1977, two physicists named Roberto Pichey and Helen Quinn proposed a solution. They introduced a new theoretical symmetry into the equations of quantum chromodynamics, the theory of the strong force. This symmetry would naturally suppress the CP violation, driving it toward zero. It was elegant. It worked mathematically, but theoretical symmetries like that don't come free. When you break a symmetry in quantum field theory, you generate a new particle. Pichey and Quinn's symmetry predicted one. Physicists Frank Wilczek and Steven Weinberg identified this particle independently and gave it a name, the axion. The name came from a brand of laundry detergent, reportedly because the particle cleaned up a messy problem in physics. That detail is either charming or distracting, depending on your perspective. Here's what matters. The axion that Pichey and Quinn's mechanism predicted would be extraordinarily light, far lighter than any particle we'd built detectors to find. It would move slowly. It would be produced in enormous quantities in the early universe. It wouldn't interact with light. It wouldn't interact electromagnetically at all. It would barely interact with ordinary matter through any channel except gravity. Run through that list of properties. Extraordinarily light, slow-moving, abundant, invisible, non-electromagnetic. That's not a description of something invented to explain dark matter. That's a description of something invented to explain CP symmetry. But it's also an almost perfect description of what dark matter requires. The axion wasn't designed to be a dark matter candidate. It just happens to fit. That coincidence is exactly why physicists find it so compelling. Detecting an axion is a different problem entirely from detecting a WIMP. WIMP detectors look for nuclear recoils. A massive particle hits a nucleus and deposits energy. That only works if the particle has enough mass to knock something around. An axion is far too light for that. You'd never see it that way. But axions have one crucial property that opens a different door. In the presence of a strong magnetic field, an axion can convert into a photon, a single particle of light. The conversion is rare, the signal is faint, but it's detectable, at least in principle, with the right instrument. The instrument built around this idea is called ADMX, the Axion Dark Matter Experiment. It works by creating an extremely strong magnetic field inside a resonant cavity, a metal chamber tuned to a specific microwave frequency. If axions of the right mass are passing through, which they should be if the axion makes up dark matter and dark matter is everywhere, some of them will convert into photons inside the cavity. Those photons can be detected. The challenge is that the axion's mass isn't precisely known. The cavity has to be tuned to match it, so the experiment slowly scans through possible axion masses, frequency by frequency, looking for a signal above the noise. ADMX has been running for years, tuning and scanning, and it has ruled out axions across an expanding range of masses. It hasn't found one yet, but the search is far from over. Several other experiments are now operating alongside ADMX, including Haystack, CAP in South Korea, and Abracadabra, which uses a different magnetic approach to probe even lighter axion masses. The technology is advancing. Quantum sensing techniques have pushed the sensitivity of these detectors to levels that would have been impossible a decade ago. Interest in axions has grown steadily as WIMP searches have come up empty. For years, the physics community had its hopes concentrated on the WIMP miracle, the elegant coincidence that pointed toward heavy, weakly interacting particles. Those searches have become extraordinarily sensitive and still found nothing. That silence hasn't proven WIMPs don't exist, but it has shifted attention. The axion now receives more serious experimental investment than it has at any point in its history. The axion remains one of the most elegant ideas in physics, a particle invented to solve one problem that might just happen to solve another entirely. WIMPs and axions aren't the only possibilities. The list of candidates is longer than most people realize, and some of them are genuinely strange. Each one represents a different set of assumptions about what dark matter could be. Each one is taken seriously by at least some physicists working in the field today. Start with sterile neutrinos. Regular neutrinos are real particles. We know they exist. They have almost no mass. They interact via the weak nuclear force, and they pass through ordinary matter almost completely unimpeded. Trillions of them are moving through your body right now, but sterile neutrinos are different. They're hypothetical cousins of the regular neutrino, heavier and even more antisocial. A sterile neutrino wouldn't interact via the weak force at all. It would respond only to gravity. That makes it essentially invisible by every measure we have. Sterile neutrinos could have been produced in the hot, dense conditions of the early universe. If they were produced in the right quantities, they would still be out there today, drifting through galaxies, holding them together without leaving any trace. One potential detection method involves looking for a very faint X-ray signal at a specific energy, 3.5 kiloelectron volts, that would result from sterile neutrinos occasionally decaying. A line at exactly that energy has been observed in some galaxy cluster data. It hasn't been confirmed. It hasn't been ruled out. It sits in that uncomfortable middle ground where science often lives for a while. Then there are primordial black holes. These are not the black holes formed when massive stars collapse at the end of their lives. Primordial black holes would have formed in the first fraction of a second after the Big Bang, when the universe was so dense and so violent that certain regions could have collapsed directly into black holes before any stars existed. The idea was proposed decades ago and was largely set aside when gravitational microlensing surveys found no evidence for a large population of them. But then LIGO detected gravitational waves from merging black holes in 2015. Some of those black holes were more massive than most stellar collapse models predicted. That unexpected observation renewed interest in primordial black holes. Could at least some fraction of dark matter be made of them? Current constraints suggest they can't account for all of it, but they haven't been entirely ruled out in certain mass ranges. It's an old idea that refuses to die completely. Self-interacting dark matter is a more recent proposal, and it comes from a specific problem. Cold dark matter predictions work extremely well on large scales. Galaxy clusters, the cosmic web, the distribution of matter across billions of light years. The standard model matches all of it. But on smaller scales, at the level of individual galaxies and especially dwarf galaxies, there are tensions. Cold dark matter simulations predict that small galaxies should have dense, spiked cores of dark matter at their centers. Observations suggest the profiles are smoother and flatter. The simulations also predict more small satellite galaxies around large ones than we actually find. These discrepancies might have ordinary explanations: stellar feedback, supernova explosions reshaping the distribution of matter. But self-interacting dark matter offers another possibility. What if dark matter particles do interact with each other, not via electromagnetism, but through some force that only operates within the dark sector? Dark matter particles occasionally colliding with other dark matter particles would smooth out those central density spikes and naturally produce the flatter profiles we observe. This model doesn't require any interaction with ordinary matter at all. That is why it's so hard to test. Ultralight fuzzy dark matter takes things in an even stranger direction. Standard dark matter particles are assumed to behave like classical particles, discrete objects with positions and momenta. But quantum mechanics tells us that every particle also has wave-like properties. For a sufficiently light particle, those wave properties become relevant at astronomic scales. Ultralight fuzzy dark matter consists of an extraordinarily light boson, potentially around 10 to the minus 22 electron volts in mass, many orders of magnitude lighter than an axion. At that mass, the quantum wavelength of the particle stretches to kiloparsec scales, the size of entire galactic cores. The dark matter wouldn't behave like a collection of particles at all. It would behave like a fluid, a continuous quantum wave spread across the galaxy's center. This naturally suppresses small-scale structure. It produces smooth cores. It limits the formation of tiny satellite galaxies. The problems that self-interacting dark matter was designed to solve would be solved here by quantum mechanics itself. These ideas span an enormous range. Sterile neutrinos have masses in the kilo-electron-volt range. Primordial black holes could be anywhere from the mass of an asteroid to many times the mass of the Sun. Self-interacting dark matter particles might resemble WIMPs in mass but carry their own hidden forces. Ultralight fuzzy dark matter particles are so light they barely qualify as particles in the conventional sense. All of them remain consistent with at least some subset of observations. None of them has been confirmed. That's the honest state of the field. The range of viable candidates, from particles billions of times lighter than an electron to objects more massive than stars, tells you something important. We genuinely don't know what dark matter is. The most direct approach to solving the dark matter mystery involves building extraordinarily sensitive detectors deep underground and simply waiting for something to happen. That might sound passive. It isn't. The engineering required to make these experiments work is some of the most demanding in all of physics. The fundamental problem is noise. Space is constantly bombarding the surface of the Earth with high-energy cosmic ray particles. At the surface, a detector sensitive enough to catch dark matter would also trigger on these cosmic rays millions of times every second. The signal you're looking for would be buried so deep under that noise that it would be completely undetectable. The only solution is to go underground. Hundreds of meters of rock overhead act as a natural shield, absorbing cosmic rays before they reach the detector. The deeper you go, the quieter the environment becomes. And quiet, in this context, is everything. The experiments that have been built inside this silence are extraordinary machines. The basic concept is straightforward. You take a large volume of some target material, surround it with highly sensitive light detectors, and wait for a dark matter particle from the galactic halo to collide with an atomic nucleus inside your target. When that collision happens, it would deposit a tiny pulse of energy. The nucleus recoils. That recoil generates a faint flash of light, or a small electrical signal, or both. Your detectors catch it, you record it, and then you spend months trying to determine whether it was a dark matter particle or just some stray background radiation that slipped through. The most widely used target material is liquid xenon. Xenon is dense, which means more atomic nuclei packed into a smaller space. It's also a noble gas, meaning it doesn't react chemically with much, which makes it easier to keep pure. Purity is critical. Any contamination introduces background signals that could mimic the signature of dark matter. The xenon in these detectors has to be cleaned to an almost absurd degree. Radioactive impurities are removed until only a handful of atoms per kilogram remain. The LUX-ZEPLIN experiment, known as LZ, sits about 1,500 meters underground in the former Homestake mine in South Dakota. Homestake is the same mine where Raymond Davis ran his solar neutrino experiment decades ago. LZ holds about 10 metric tons of liquid xenon as its active target. It's surrounded by photomultiplier tubes that can detect individual photons of scintillation light. The entire detector is submerged in a tank of water to provide additional shielding from radiation in the surrounding rock. The water itself has to be purified. The tank walls have to be chosen for low radioactivity. Even the researchers who work on these detectors have to be careful about what they bring into the clean environment. In Italy, under the Gran Sasso Mountain, the Xenon collaboration has been running a sequence of progressively larger detectors. XENON-1T held about 3.5 tons of xenon. Its successor, Xenont, scaled up to roughly 8 tons. Each generation has pushed sensitivity further. In China, the PANDAX4 trillion experiment operates under the Jinping Mountain in Sichuan province, beneath about 2,400 meters of rock, one of the deepest underground laboratories on Earth. PANDAX4 trillion uses 4 tons of liquid xenon as its active mass. Not every experiment uses xenon. The cryogenic dark matter search, known as CDMS, takes a different approach entirely. It uses germanium and silicon crystals, cooled to temperatures within a fraction of a degree of absolute zero. At those temperatures, a tiny nuclear recoil produces measurable vibrations in the crystal lattice, called phonons, alongside an electrical signal. Measuring both simultaneously allows the experiment to distinguish nuclear recoils from electron recoils, which is how you separate potential dark matter events from most background sources. The detectors have grown enormously over time. Early xenon experiments in the 1990s worked with a few kilograms of target material. Today's detectors work with multiple tons. That's a factor of roughly 1,000 in target mass over 2 to 3 decades. Sensitivity to the interaction rate has improved by a factor of more than 1,000,000. Each improvement should have been enough to catch a WIMP if WIMPs interact at the rates the most natural theoretical models predicted. Here's what's happened instead. Nothing. No confirmed detection across any of these experiments. Not one event that couldn't be explained by a known background source. That null result is important information. Each time a detector runs and finds nothing, it rules out a portion of the possible parameter space for WIMPs. If a WIMP had a certain mass and interacted with ordinary matter at a certain rate, we would have seen it by now. The allowed region where WIMPs could still be hiding has shrunk dramatically. The most natural WIMP candidates, the ones theorists found most compelling 20 years ago, are now excluded. They would have shown up already. The experiments keep searching, but they're searching in territory that the simplest theoretical models didn't predict would be empty. There's a phrase physicists use: closing the window. Each experiment closes the window on another part of the possible WIMP landscape. The window is much smaller now than it was. It's not fully closed. There are still ranges of WIMP mass and interaction strength that haven't been tested yet. Going lighter in mass requires different detector technologies. Going to very low interaction rates requires even larger, even quieter detectors. Both directions are being pursued. What these experiments have demonstrated, beyond any doubt, is that if dark matter does interact with ordinary matter through anything other than gravity, it does so extraordinarily rarely. The galactic halo is thought to contain roughly 1 billion dark matter particles passing through every square meter of Earth every second. Through you, right now, if the models are correct. And yet none of these detectors, across decades of operation, have caught one. Every year the detectors grow more sensitive, the targets get larger, and the silence becomes harder to explain. If dark matter particles can't be caught colliding with ordinary matter in an underground lab, maybe they can be caught annihilating each other. Here's the idea. Some dark matter candidates, WIMPs in particular, are thought to be their own antiparticles. That means when two of them meet, they don't just pass through each other, they annihilate. They destroy each other completely, converting their combined mass into energy. That energy has to go somewhere. It comes out as gamma rays, or positrons, or neutrinos, particles that travel in straight lines across the galaxy and can, in principle, be detected here on Earth. This is indirect detection. You're not looking for the dark matter itself. You're looking for the debris it leaves behind when it runs into itself. The logic is sound. If dark matter is densely packed in certain regions of the universe, annihilation events should happen more frequently there. The galactic center is the obvious target. The core of the Milky Way has an enormous concentration of mass, and if dark matter follows the distribution that simulations predict, it should be piled up there too. More dark matter in a smaller volume means more collisions. More collisions means more annihilation. More annihilation means more gamma rays streaming outward in every direction. The Fermi Gamma Ray Space Telescope has been in orbit since 2008, scanning the entire sky for exactly these kinds of signals. It's a remarkable instrument. It maps gamma rays across the whole sky continuously, building up a picture of where high-energy radiation is coming from. and what energies it carries. And when astronomers pointed it at the galactic center, they found something, a real signal, an excess of gamma rays with energies around 20 GeV, concentrated in a roughly spherical region around the Milky Way's core. The spectrum of that excess, the specific distribution of energies, matches what you would expect from WIMP annihilation remarkably well. A WIMP with a mass around 500 times that of a proton annihilating with another WIMP would produce gamma rays at almost exactly those energies. The match is striking, but here's the problem. The galactic center is one of the most complicated regions in the sky. It is packed with ordinary astrophysical sources: pulsars, supernova remnants, molecular gas clouds, stellar winds, magnetic fields, all of them producing radiation. Separating a dark matter signal from that background requires knowing what all those sources are doing, which requires models, and models have assumptions, and assumptions can introduce errors. A population of millisecond pulsars, rapidly spinning neutron stars that emit gamma rays in tight repeating pulses, could produce a diffuse gamma ray excess that looks nearly identical to what you'd expect from dark matter annihilation. There are likely thousands of them near the galactic center, too faint to resolve individually, but collectively bright enough to mimic the signal. Some analyses favor the pulsar explanation. Others argue the spatial distribution fits dark matter better. Nobody has closed the argument. That's why astronomers also look at dwarf spheroidal galaxies. These are small, faint satellite galaxies orbiting the Milky Way. They have very little gas. They formed almost no stars in recent history. There are almost no pulsars, no supernova remnants, no hot plasma, almost nothing that produces gamma rays through ordinary astrophysical processes. But they have enormous amounts of dark matter relative to their visible mass. Some dwarf spheroidals are estimated to be more than 99% dark matter by mass. If dark matter annihilates, these galaxies should glow faintly in gamma rays with almost no competing background. They are cleaner targets. Fermi has observed dozens of them. So far, no excess has been detected. Each null result from a dwarf galaxy tightens the constraint on how strongly W back. IMPs can annihilate, and those constraints are starting to squeeze the same WIMP parameter space that underground detectors are squeezing from a different direction. Neutrinos offer a third channel. The sun has been sweeping through the galaxy for 4.6 billion years. Dark matter particles passing through the solar system can occasionally scatter off nuclei in the sun and lose enough energy to become gravitationally trapped. Over billions of years, those particles accumulate in the sun's core. Eventually, the density builds high enough that annihilation becomes frequent. The neutrinos produced in those annihilations, unlike gamma rays, pass straight through the sun without being absorbed and stream outward in all directions. The Ice Cube Neutrino Observatory, buried more than a kilometer deep in the Antarctic ice sheet, looks for exactly these neutrinos. It has found no excess coming from the direction of the sun. Again, a null result, another constraint, another door closed a little further. Each of these approaches is genuinely careful science. The researchers involved are not being sloppy. They understand the backgrounds. They account for the systematics. They know how to distinguish a real signal from statistical noise, at least in principle. But the universe doesn't always cooperate. The galactic center excess is real, and it remains unexplained. It might be dark matter. It might be pulsars. It might be something else entirely that nobody has thought of yet. The signals have been tantalizing but not definitive, and tantalizing but not definitive has been the story of dark matter research for a very long time. There's a third approach to finding dark matter, and it's the most audacious of all. The first two approaches are fundamentally passive. Underground detectors sit and wait for dark matter to arrive from space. Space telescopes scan the sky for signals produced when dark matter destroys itself. Both of those strategies assume dark matter is already out there, moving through the galaxy, and that we just need sensitive enough instruments to catch it. The third approach is different. Instead of waiting for dark matter to come to us, we try to make it ourselves. That's what particle accelerators do. They take ordinary matter, accelerate it to extraordinary speeds, and smash it together. The collisions release enormous amounts of energy. That energy converts into particles, new particles, particles that don't exist in stable form anywhere in the everyday world. It happens in fractions of a second, inside detectors the size of cathedrals, buried under the French-Swiss border near Geneva. The machine is called the Large Hadron Collider. It's the most powerful particle accelerator ever built. At the LHC, protons travel through a ring 27 kilometers in circumference. They reach speeds approaching the speed of light. Two beams travel in opposite directions, and at specific points along the ring they intersect. When they collide, the energies involved approach conditions that existed in the early universe, fractions of a second after the Big Bang. If dark matter particles can be produced at all, the thinking goes, this is where it would happen. Here's the problem. Dark matter doesn't interact with light. It doesn't trigger electrical signals. It passes through ordinary matter almost entirely without effect. If a dark matter particle is created in one of these collisions, it will simply pass through the detector and disappear. You can't catch it. You can't see it. It leaves no mark. But it does leave a gap. Every collision is subject to conservation laws. Energy and momentum going in must equal energy and momentum coming out. Physicists can measure everything that comes out of a collision. They can account for every particle, every trajectory, every energy deposit. If the numbers don't add up, if there's energy and momentum missing from the final tally, something left without being detected, that something is a candidate for dark matter. Physicists call it a missing energy signature. It's an absence that points to a presence. The two main detectors at the LHC, ATLAS and CMS, are designed to catch exactly these events. Both detectors are massive. Both are extraordinarily precise. They can track thousands of particles emerging from a single collision and reconstruct what happened in a tiny fraction of a second. They look for events where the accounting fails, where the numbers don't balance, where something escaped. This approach proved itself in 2012. That year, the LHC found the Higgs boson. The Higgs had been predicted by theory for nearly 50 years. It had never been directly detected. The LHC found it buried inside billions of collision events, a signal barely distinguishable from background noise. That discovery demonstrated something important. This machine can genuinely find new particles. It's not just theoretical, it works. So when physicists began searching for supersymmetric particles, there was real optimism. Supersymmetry is a theoretical framework that extends the standard model of particle physics. It predicts that every known particle has a partner particle, a heavier counterpart with slightly different properties. The lightest of these supersymmetric partners, a particle called the neutrino, would be massive, stable, and would interact only through gravity and the weak nuclear force. That's almost exactly the property profile dark matter needs. The neutrino was the most natural WIMP candidate in all of theoretical physics. Finding it at the LHC would have solved the dark matter problem and confirmed supersymmetry in a single result. The LHC ran, the collision energies went up, the data piled up, billions of events were analyzed, missing energy signatures were cataloged and examined, and the neutrino never appeared. Neither did any other supersymmetric particle. The simplest versions of supersymmetry, the ones that most naturally predicted a WIMP at the mass ranges the LHC can probe, have now been ruled out. Not supersymmetry as a whole, which remains mathematically possible in more complex forms, but the versions that were most compelling, most elegant, most directly connected to the dark matter problem. Those have been pushed aside by the data. This doesn't mean the LHC failed. It returned extraordinary science. It found the Higgs. It measured particle interactions with stunning precision. It's still running. Higher energies are still possible. Supersymmetric particles at heavier mass scales remain theoretically viable, and future upgrades may probe those regions. But the straightforward prediction, the one physicists were most excited about, the one that would have neatly resolved decades of mystery, didn't pan out. So far, the LHC has found nothing. Before we go any further, it's worth asking a harder question. We've spent a lot of time talking about detectors and particle candidates and experiments that keep coming up empty, but there's a more uncomfortable possibility sitting underneath all of that. What if there is no dark matter? What if we've been chasing a particle that doesn't exist? What if the problem isn't missing mass, but a broken theory of gravity? That's not a fringe idea. It has a name, a founding paper, and a community of serious physicists behind it. In 1983, an Israeli physicist named Mordechai Milgram proposed something called modified Newtonian dynamics, usually shortened to MOND. The premise is straightforward. Newton's law of gravity works extraordinarily well in most situations, but Milgram noticed something. The rotation curve problem, flat curves, stars at the edges of galaxies moving too fast, only appeared at very low accelerations. Specifically, accelerations far below anything we routinely measure on Earth or even within our solar system. Milgram proposed that at those extremely low accelerations, gravity doesn't quite behave the way Newton's formula predicts. It falls off more slowly. The force stays stronger at large distances than standard gravity would allow. That's the entire modification. Below a certain acceleration threshold, roughly 1.2 times 10 to the negative 10th meters per second squared, gravity works differently. Above that threshold, you get normal Newtonian behavior. Below it, you get something else. Here's what makes MOND genuinely impressive. You take a spiral galaxy. You measure the visible matter, the stars, the gas, the dust. You plug those numbers into MOND, and out come rotation curves that match observations, often with remarkable accuracy, using no free parameters beyond what you can see. No dark matter halo, no invisible mass distribution, just the visible matter and a modified force law. For many spiral galaxies, MOND fits the data better than dark matter models do. That is not nothing. That's the kind of result that earns a theory some respect. There's even a deeper pattern called the baryonic Tully-Fisher relation, which connects the total visible mass of a spiral galaxy to how fast its outer stars orbit. MOND predicts this relationship naturally. Dark matter models have a harder time explaining it, because you'd expect the ratio of dark matter to ordinary matter to vary from galaxy to galaxy. MOND says that ratio doesn't matter, the visible mass is all you need. And for spiral galaxies, that prediction holds up surprisingly well. So why doesn't the entire physics community switch to MOND and move on? Because MOND fails, and it fails badly in ways that are very hard to patch. Start with galaxy clusters. Remember Zwicky back in 1933, finding that the Coma Cluster was moving too fast to be held together by its visible mass? MOND helps, but it doesn't solve the problem. Even with the modified force law, galaxy clusters still require additional mass beyond what's visible. MOND reduces the discrepancy but doesn't eliminate it. You still need something extra. So MOND doesn't actually remove the need for dark matter entirely. It just moves the goalposts. Then there's the bullet cluster. Two galaxy clusters collided. The ordinary matter, hot gas glowing in X-rays, slowed down and piled up in the middle. The gravitational lensing signal, the region where most of the mass actually is, traveled ahead of the gas. The mass and the visible matter are physically separated in space. MOND is a modification to how gravity behaves. It doesn't separate mass from matter. It can't explain why the gravitational signal is sitting in a different place than the stuff generating it. The bullet cluster is one of those observations that is genuinely difficult to square with any purely modified gravity picture. Then there's the cosmic microwave background. The CMB power spectrum, those peaks and troughs encoding the composition of the early universe, requires cold dark matter to fit. The positions and heights of those acoustic peaks depend on the ratio of ordinary matter to something that behaves like dark matter. Without dark matter, the peaks look completely different. MOND has no natural mechanism to reproduce the CMB pattern. Relativistic extensions of MOND, the most serious of which is a theory called TeVs, proposed by Jacob Bekenstein in 2004, were constructed specifically to handle situations where special and general relativity matter. TeVs can reproduce some CMB features, but only by introducing additional fields and free parameters. The elegance that made MOND appealing gets buried under theoretical scaffolding. And even then, the fit is poor compared to the standard cold dark matter model. The situation gets worse. Gravitational wave observations from colliding neutron stars in 2017, an event detected by both LIGO and the Fermi telescope, allowed physicists to measure whether gravitational waves and light travel at the same speed. They do, to extraordinary precision. Some versions of TeVs predicted they shouldn't. That measurement ruled out a significant class of relativistic MOND theories almost overnight. What's left is a theory that works impressively for spiral galaxies, struggles with galaxy clusters, fails to account for the CMB without adding dark matter anyway, and has watched its most sophisticated relativistic extensions run into serious observational constraints. The mainstream scientific view is that MOND is probably capturing something real about the behavior of dark matter on galactic scales, some pattern in how it distributes itself relative to ordinary matter. But it almost certainly isn't the whole story. Some researchers are exploring hybrid models, where dark matter exists but has properties that naturally produce MOND-like behavior in certain regimes. That's an active area of work. The rotation curve success of MOND isn't something dark matter theorists can just ignore. It's pointing at something. What exactly, no one agrees on yet. Modified gravity hasn't been killed off entirely, but it's on life support. Dark matter isn't just something that holds existing galaxies together. It built them. It laid the groundwork for every galaxy, every star, every atom of ordinary matter that ever coalesced into something recognizable. To understand how, you have to go back to the very beginning. In the first moments after the Big Bang, the universe was extraordinarily uniform, almost perfectly smooth in every direction. But not quite. There were tiny fluctuations in density, quantum variations so small they seem almost irrelevant. One region had a slightly higher concentration of energy than its neighbor. Another was slightly emptier. These differences were on the order of 1 part in 100,000, by any measure vanishingly small. And yet, those tiny wrinkles in the fabric of the early universe became everything. Here's the problem. In those early moments, ordinary matter was locked in a kind of cosmic struggle. Radiation pressure, the outward push of photons, prevented it from clumping. Protons, electrons, and light were all tangled together in a hot, dense plasma. Whenever ordinary matter tried to collapse under gravity, radiation pushed back. It couldn't settle. It couldn't condense. It kept sloshing back and forth like water in a bathtub, unable to hold a shape. On its own, ordinary matter couldn't have built the structures we see today. The fluctuations were too small. The radiation pressure was too strong. The universe would have spread out too evenly. You'd end up with a cosmos that's essentially featureless. No galaxies, no stars, no planets. Dark matter changed that completely. Dark matter doesn't interact with light. Radiation pressure meant nothing to it. While ordinary matter was being pushed around, dark matter was already responding to gravity, already beginning to clump around those tiny density fluctuations. It didn't wait. It started collapsing almost immediately after the Big Bang, long before ordinary matter had any chance to do the same. Over millions of years, dark matter gathered into structures, halos, and then ordinary matter, finally freed from the plasma state when the universe cooled enough for electrons and protons to combine into neutral atoms, had somewhere to fall. Think about what that means. The dark matter halos were already there, waiting. Gravity pulled ordinary matter into them. Gas clouds fell into dark matter wells and began to compress. As the gas compressed, it heated up. When it got hot enough, nuclear fusion ignited. Stars were born. And stars, gathered in enormous numbers inside those same dark matter halos, became galaxies. This is why astronomers say dark matter got a head start. Without it, the density fluctuations in ordinary matter alone would have been too weak to overcome the smoothing effects of radiation. The universe would have expanded too uniformly. Structures on the scale of galaxies would have been incredibly slow to form, or might not have formed at all within the age of the universe. The math doesn't work without dark matter seeding the process first. The evidence for this is striking, and it comes from computer simulations. Over the past few decades, cosmologists have built incredibly detailed simulations of cosmic structure formation. They feed in the initial conditions of the early universe, the tiny density fluctuations, the expansion rate, the physical laws, and let the simulation run forward for 13.8 billion years. When those simulations include cold dark matter, the result looks like our universe. Galaxy clusters connected by long filaments of gas and dark matter. Enormous empty voids between the filaments. The cosmic web, as astronomers call it, emerges naturally. When the same simulations are run without dark matter, the result looks completely different. The structures that form are wrong in almost every way. The filaments don't appear. The galaxy clusters don't match. The voids are too small. The universe that emerges bears almost no resemblance to the one we actually live in. Cold dark matter isn't just a convenient addition to the model. It's load-bearing. Remove it and the whole structure collapses. Look at the Milky Way. The galaxy we live in sits inside a dark matter halo estimated to extend somewhere between 300,000 and 600,000 light-years from the galactic center. The visible disk of stars, everything you can see on a clear night, occupies only a fraction of that volume. The dark matter halo is far larger than the galaxy it contains. That halo wasn't built after the Milky Way formed. The halo came first. Ordinary matter fell into it. The halo is the reason the Milky Way exists at all. The same is true for every galaxy we've ever observed. Each one sits embedded in a dark matter halo that formed early, grew through mergers with smaller halos, and continuously shaped the distribution of gas and stars within it. The cosmic web of filaments connecting galaxy clusters is a dark matter web, traced by the ordinary matter that followed it. Every image from the Hubble Space Telescope, every galaxy cataloged in surveys covering billions of light-years, represents ordinary matter that was guided into place by invisible structure that formed first. The universe we see is the universe that dark matter built. Without dark matter, the gravitational seeds that grew into galaxies would never have been planted, and you almost certainly wouldn't exist. We've spent nearly a century trying to figure out what dark matter is. Zwicky saw the first hint in 1933. Rubin made it impossible to ignore in the 1970s. The bullet cluster showed us dark matter and ordinary matter physically separating. The CMB encoded its presence in the oldest light in the universe. And still, after all of that, we have never directly detected a single dark matter particle. Not one confirmed signal. Not one definitive result. The search is still ongoing, and it's entering its most sensitive phase yet. The most advanced direct detection experiments on Earth right now are running at a scale that would have seemed impossible a decade ago. LZ, the LUX-ZEPLIN experiment, sits nearly a mile underground in the Homestake Mine in South Dakota. It uses about 10 metric tons of liquid xenon as its target material. When a dark matter particle from the galactic halo passes through that xenon and strikes an atomic nucleus, it should produce a tiny flash of light and a small burst of ionization. Photomultiplier tubes surrounding the tank would catch that signal. The detector is sensitive enough to register interactions at energy scales far smaller than anything previous experiments could reach. LZ has been collecting data, and the allowed parameter space for WIMP dark matter keeps shrinking. Xenon at the Gran Sasso Laboratory in central Italy is running at similar scales. It uses roughly 8 metric tons of liquid xenon and has achieved some of the lowest background noise levels ever recorded in a dark matter detector. Both experiments are pushing into territory where, if WIMPs exist at the masses and interaction strengths that theoretical models predicted most confidently, they should be appearing. The fact that they haven't doesn't prove WIMPs don't exist, but it does rule out many of the simplest, most elegant versions of the idea. Axion searches are accelerating too. The ADMX experiment, the Axion dark matter experiment, uses a resonant microwave cavity inside a powerful superconducting magnet. The basic idea is that axions passing through a strong magnetic field should occasionally convert into photons. The cavity is tuned to specific frequencies. Researchers slowly sweep across a range of possible axion masses, listening for that conversion signal. Upgraded versions of ADMX are operating with better sensitivity than ever before. New experiments using different resonant cavity designs are coming online alongside them. The axion mass range is vast, covering many orders of magnitude. Systematically searching across all of it will take time, but the tools are getting sharper every year. The picture gets even larger when you look at what's happening in astronomy. The Vera Rubin Observatory in Chile will conduct the deepest, widest survey of the sky ever attempted. Over a decade, it will photograph billions of galaxies and use the statistical patterns of gravitational lensing across those images to map dark matter distribution with extraordinary detail. Rubin herself spent her career measuring the rotation curves that made dark matter unavoidable. It says something that the most powerful lensing survey ever built carries her name. The observatory won't detect dark matter particles directly. What it will produce is the most complete map ever made of where dark matter is and how it's structured. From individual galaxy halos out to the largest filaments in the cosmic web, the Square Kilometre Array, a radio telescope being built across sites in South Africa and Australia, will study galaxy rotation curves across cosmic time, not just nearby galaxies. Galaxies as they existed billions of years ago, when the universe was young and structures were still assembling. It will give astronomers a record of how dark matter has shaped galaxy formation across nearly the full history of the universe. That kind of data has never existed before. The Roman Space Telescope, NASA's next major space observatory, will use weak gravitational lensing to measure dark matter on cosmological scales, mapping how it's distributed across enormous volumes of space with a level of precision that ground-based telescopes can't match. Here's what genuine detection would actually mean. It wouldn't just fill in a blank on a chart. It would represent the discovery of an entirely new form of matter, something outside the standard model of particle physics, something that has shaped every galaxy and every structure in the observable universe without ever leaving a mark we could identify. It would be one of the most significant scientific discoveries in human history. It would open questions about what other invisible components of reality we've been missing, how deep the unknown really goes. That hasn't happened yet. Decades of increasingly sensitive experiments have returned silence. Each null result is real data. Each one constrains the possibilities and forces theorists to revise their models. The search continues. Not because scientists are ignoring the negative results, but because the evidence for dark matter's existence is overwhelming. The only reasonable response to a mystery that well established is to keep looking, with better tools, deeper underground, and further into space, somewhere in a laboratory, deep underground, or in the data streaming down from a telescope in orbit. The answer might already be hiding. Think about what it means to have built an accurate model of the universe while openly admitting we don't know what most of it is. The Lambda CDM model, the standard cosmological model, predicts the structure of the universe with extraordinary precision. It matches the CMB. It matches rotation curves. It matches gravitational lensing maps. It matches the large-scale distribution of galaxies across billions of light years. And at the center of all that predictive success sits a substance nobody has ever directly detected. That's not a flaw in the model. That's just where we are. Every atom in your body is ordinary baryonic matter. Every star you can name. Every galaxy and every Hubble image ever taken. All of it. Everything humanity has ever seen or touched or measured sits inside that 5% sliver. The other 27% is dark matter, something real, something massive, something gravitationally dominant, and something completely unknown. It's not hiding behind a star. It's not too far away to photograph. It passes through you right now, constantly, without leaving any trace at all. That number is worth sitting with, 5%. Not a rounding error, not a small correction. The visible universe, the thing we built all of physics and chemistry and astronomy to describe, is the minority. It always has been. We just didn't know it. What's strange is how confident we are about something we've never seen. Astronomers don't speculate that dark matter is probably there. They measure it, they map it, they track how it shaped the formation of every galaxy in the observable universe. The dark matter halo around the Milky Way extends hundreds of thousands of light years beyond the visible disk of our galaxy. It was there before the first stars formed. In a real sense, it built the structure that stars and planets and people eventually grew inside, and yet we can't point to a single particle and say, that's it. We've never captured one, never triggered a detector, never produced one in a collider. We've built enormous experiments and driven them deep underground and waited years in complete silence. The silence keeps getting louder. There's something worth recognizing in that. Astronomers can't travel to the Coma Cluster. They can't fly out to Stephenson 218 or land on a neutron star. Everything we know about the distant universe comes from light, from radiation that traveled millions or billions of light years before landing on a telescope mirror. We've always been reading shadows. We've always been inferring the thing itself from the signal it sends ahead of itself. Dark matter is just the extreme version of that. No signal at all, only the shape it carves in everything around it. Fritz Zwicky saw it in 1933 in the velocities of galaxies moving too fast. Vera Rubin saw it in rotation curves that refused to fall off the way Newton said they should. The bullet cluster showed it spatially separated from ordinary matter like two ships passing through each other. The CMB encoded it in temperature fluctuations, 1 part in 100,000. Every independent line of evidence points to the same invisible thing. That convergence doesn't happen by accident. So here we are, the most successful cosmological model ever constructed, verified across scales from individual galaxies to the entire observable universe. And the dominant component of that model is a placeholder, a name we gave to a gravitational effect we can measure but cannot explain: dark matter. Dark not because it's hidden, not because it's mysterious in some theatrical sense, but because it produces no light at all. It sits completely outside the electromagnetic spectrum. It doesn't glow, it doesn't absorb, it doesn't reflect, it just pulls. The universe doesn't owe us comprehension. It didn't arrange itself for our convenience or design its fundamental constituents to be detectable with human instruments. We happen to evolve on one planet, developed mathematics and telescopes and underground xenon detectors, and started asking questions the universe isn't obligated to answer cleanly. Maybe that's the most honest thing science has ever produced, a precise map of the shape of something we cannot see, drawn entirely from the way everything else bends around it.